Hello class. Right now what I want to do is I want to go over with you how to construct a polynomial series if we're given some initial conditions for a polynomial. This is important to understand so that we can construct polynomials that will approximate functions that we know that exist on our calculator and that we use every day in calculus. So what we're going to do is we're going to start off with this task where we want to construct a polynomial of the general form of a polynomial, where we have actually, if you look at the polynomial here, it goes up to the fourth order, and we have four derivatives. We have the function at 0 and each of four derivatives at 0 as center points. So we want to construct the polynomial that will match these conditions. And if we can do that, we can extend this further and teach how, or show you guys how we would construct a polynomial for any function using this method. So our first step is to take the polynomial, and I'll just rewrite it as the general form, which is a0 plus the second coefficient, the first power, plus the next one, plus the third times x to the third, plus the fourth times x to the fourth. So when we take its first derivative, the first derivative of x will be a sub 1 plus 2 times a sub 2 x to the first power, plus 3 times x squared. A3 times x squared plus 4 times a sub 4 times x to the third power. We'll go on and we'll do this for the next couple derivatives, and we'll find out that that becomes 0. This becomes 2a to the second plus 6a sub 3 times x plus 12a sub 4 times x squared. The next derivative will be the third derivative. That will be 0 for that part, plus 6a to the third plus 24a to the fourth x. And we'll do the fourth derivative, which will be 0 for that part plus 24a to the fourth. So now, using our initial condition, we can solve for each one of these. For instance, I'll just label these equations 1, 2, 3, 4, and 5. I'm going to use equation 1, and I'm going to say that when I know that the polynomial at 0 has a value at 1. And when I put in, when I solve for a sub 0, and I notice that all of the other terms, because the polynomial is centered at 0, I can directly solve for my first coefficient, and that's just 1. Now when I use the next equation, I have the derivative at 0, which from the initial conditions before, let me zoom out so you can see that. Okay, says that the next derivative at 0 is equal to 3, which I'll set equal to my second derivative in equation 2. So that says a1 plus, and then all the other terms are 0. So a1 equals 3. I'll use equation 3 with the second derivative, which said that was equal to 5. So if you look at equation 3, I have two a2's, a sub 2, plus all the other terms turn out to be 0 because it's centered at 0. And that results in a2 equaling 5 over 2. And then I'll keep working on this. The next part says that the third derivative at 0 is equal to it's equal to 7, which is equal to 6a to sub 3 plus 24a sub 4 times 0. So again, a sub 3 is easy to solve for. That's just 7 over 6. And then the last one says the fourth derivative at 0 is equal to 9, which is equal to 24a to the fourth, using equation 5. And that says that the fourth coefficient is going to be 9 over 24. With these values, I'm just going to list them here. A sub 0 was 1, a sub 1 was 3, a sub 2 was 5 over 2, a sub 3 was 7 over 6, and a sub 4 was 9 over 24. If you look at this when we assemble our polynomial, because remember our original polynomial structure was a0 plus a1x plus a2x squared plus a sub 3x cubed plus a sub 4x the fourth. When we assemble our polynomial, we end up getting an interesting pattern. And what this means is, if you notice, all of our initial conditions are shown as coefficients. And the other thing that's interesting is because the nature of taking a derivative of a string of polynomials, we get in the denominator, if you notice, I can rewrite this where I'll have the coefficient, or the the function's value at 0 times x sub 0 over, this is a zeroth derivative, which would be the function, over 0 factorial, plus the next term would be the derivative term, the first derivative at 0 times x the first over 1 factorial, plus the next term would be the next derivative, which was 5 at 0, x squared over 2 factorial, plus there's a pattern to this, which is really what's interesting about using polynomials to model any function, is now you get the third derivative at 0, which is the 7 value, x cubed, and there's this really neat pattern. It's not 6, this would be 3 factorial, and the last one is going to be the fourth derivative at 0, x the fourth over 4 factorial. And if we had more terms, we could just continue the pattern. It'd be the fifth derivative times, at the center point of 0, times x the fifth over 5 factorial, and so on. So what we have here is a formula so that for any function we're trying to model with a polynomial, as long as we can take their derivatives, we can come up with what the polynomial would be to match, which would be, since this is a sum of infinite terms, well, in this case it's 5 terms, so well, I added that term on the end just to demonstrate. But if we start at 0 and go to 4, then we have the nth derivative centered at 0 times our polynomial at its nth power over n factorial. And this is the general form for finding a polynomial to match any function. This can be any function, and in my next video what I'm going to show is how we handle any function using this polynomial technique. And this happens to be right here a Taylor polynomial. That's what the special name for it. And this one happens to be centered at x equals 0, which in this case has a special name. It's called a Maclaurin series. Now in my next video, what I intend to do is show you how we can model any function using this string of polynomials, and some really interesting things happen. So I want you to tune into that. But I've kind of reached my allotment on YouTube time here, so I'm going to end the video now, and I'll come back and start up talking about how we do a Taylor polynomial for any function of our choosing. Take care.